So unfortunately, during the presentation time, we can't have booth time in here, so everybody please take your seats, and we have the online participants who have to get our schedule too, so I can see everybody slowly moving. That's good. We have now the second presentation that discusses the topic of service-oriented architecture. We have Thomas Galla and Michael Ziehensack from Elektrobit who are going to present. And one question to you, has any one of you been at the first Ethernet and IP Tech Day? Michael, you have, right? I thought you had, but not with the presentation at the time. So, I hope I'm allowed to call you a veteran of Automotive Ethernet then. And Thomas, you too. I know you've been working with it for a long time as well. So I'd like to welcome these speakers, and everybody enjoy the presentation.
Okay, so good to see a lot of you again face-to-face after almost 2 years of COVID-19. In our presentation, we want to talk about time-sensitive control data streams in a service-oriented architecture based on Automotive Ethernet. But actually, before we start to talk about communication protocols and communication software, I would like to start with a concept that is mandatory on highways in Austria and Germany. It's called Rettungsgasse. So, in normal traffic conditions, any vehicle can use all the lanes of the highway. So there is no permanently reserved lane for an emergency vehicle. Just if a traffic jam builds up, or in case of a traffic jam, then an ad hoc emergency lane is created, the Rettungsgasse, as you can see on the screen here. So the normal vehicles move to the left and move to the right, and space is made for the really important things. And yeah, that's a pretty nice concept, a pretty efficient concept. So, which works and have space for emergency vehicles, even in case of a traffic jam, and even if there's no permanently reserved lane. Actually, give way to important things. That's what we also need and want to have for time-critical applications in our network. And with that introduction, I would hand over to my colleague Tom, who will talk a bit more about time-critical applications.
Okay, thanks a lot, Michael. But before going into time-critical application, let's first have a short recap, okay, what service-oriented architectures are about. I'm gonna keep this rather brief because we already had the talk of Stellantis on this topic today. So, central ingredient of service-oriented architectures are services, which are discrete units of functionality that can be accessed remotely and deployed and updated independently of other services. Applications, in the end, are built by combining those services, like the example on this slide where we have a distributed control loop application which is built out of a sensor service, a controller service, and an actuator service. The binding between the server and the client is usually established dynamically by means of service discovery. So this basically means that the client searches for services by sending service find messages, the server offers services by transmitting service offer messages, and finally the client subscribes to event notifications of an offered service by means of event subscription messages. In case of method communication, we have something similar. Only difference is that instead of registering for event notifications by event subscriptions, we could do something similar by method reservation to, for example, reserve bandwidth for method communication. This dynamic binding between client and server is the key ingredient to actually provide scalability and allow for adding new service users without any adaptation of existing service providers. If we now take a look at the interaction between the controller service and the actuator service, on the previous slide this was realized by method communication. As an alternative realization possibility, this could also be done by means of service events instead of methods. If we do it that way, then basically the only major difference is that the client-server roles between the controller and the actuator service are effectively swapped. Perhaps a note at this point in time, the examples that we're going to provide in this presentation, the concepts that we are going to show, those actually focus on the scenario with realization by means of service events, but all the concepts that we show here basically also apply to method communication with, albeit some smaller adaptation required. Okay, but now let's add a little bit time sensitivity to the whole picture. So if we now look at advanced driver assistance functions or automatic driving functions, or also chassis applications, those are usually time-critical systems, and they use time-sensitive control data streams for interaction amongst the different services. So coming back to the control loop example, this means that the server provides service event notifications with a defined update cycle, and on the other hand side, the client needs service events with a defined update cycle and with a maximum bounded latency. Meaning, server, for example, sends sensor data every 10 milliseconds. The client needs the sensor data with a maximum age of, for example, 5 milliseconds and an update rate of 20 milliseconds. So this means from the network perspective, we have to ensure that the event notifications are sent every 10 milliseconds with an upper bounded latency of 5 milliseconds. Good news here is Automotive Ethernet networks together with TSN capabilities are already capable of guaranteeing maximum bounded latencies for control data streams here by effectively separating the streams in up to 8 different traffic classes and applying traffic shaping by means of priority-based shaping, credit-based shaping, or even time-aware shaping amongst the different classes. The interesting point here, however, is it's not sufficient to just look at the application and on the network. So we have to expand the model a little bit by introducing additional layers in between. And now, moving from top to bottom, let's start with the middleware layer. The middleware, communication middleware, effectively implements the OSI layers 5 to 7. And especially in a time-sensitive, service-oriented architecture, it's also in charge of negotiating things like event update cycles and latencies dynamically between the client and the server, probably as part of the service discovery phase. Second job of the middleware is actually to provide an environment for separated communication channels of different priorities. This can usually be done by creating dedicated sockets on a POSIX-based operating system, for example, and assigning appropriate priorities to those different sockets. And then when actually operating, sending, receiving data on those sockets, to use priority-based algorithms to operate on this data. Next job of the middleware is, once this environment has to be set up, is to select an appropriate priority based on the desired maximum latency for a particular data transmission. Once this priority has been selected, the middleware is in charge of actually checking whether this priority is effectively supported by the provided environment. And if this is the case, then the job of the middleware is to request bandwidth for the interaction amongst the different services on all involved network elements, basically meaning on all intermediate switches and also on the end nodes. This bandwidth reservation is something which is delegated towards the communication stack, which Michael is going to talk about in a few seconds. And finally, the last job of the middleware is to report success or failure of all of the previous steps, including the bandwidth reservation, towards the client application.
Thank you. Yeah, there are 2 more layers. So the ComStack layer just below the communication middleware. So the COM stack layer implements the OSI layers 3 to 4 and partly also layer 2. And it consists of a network stack, so that's where the protocols like UDP and IP are implemented, and also the network drivers that take care of the communication hardware. The communication stack also provides an environment for prioritized channels. So there are network sockets, and these network sockets gets a priority assigned, and the interaction between COM stack and COM middleware is done according to this priority. The communication stack also, let's say, takes care that related bandwidth is reserved on all devices in the network on request from the COM middleware. And it also selects the VLAN BCP field, so to set the related priority from the network socket also in the BCP field. And then finally it selects the priority queue of the communication hardware. And of course that's in both directions, so the transmission side and the reception side. Okay, the last layer, the final one, so the communication hardware. It consists of the communication controllers, the transceivers, and all the Ethernet switches on the network. And this means it implements the layers 1 and 2. And yeah, I would say that's the home base, or where the key features of most of the TSN protocols are implemented, like the hardware timestamping for this 8221 ES for time and synchronization, or the credit-based shapers are implemented, like CBS or time-aware shapers. What I should mention is that when you see these different layers, is that they interact with each other, but they're basically independent. And another thing we need to distinguish is a certain protocol standard and a protocol implementation. So if one claims that one communication hardware standard perfectly supports quality of service, then this by definition means it's only the green layer, okay? So please don't get confused with protocol standards, protocol implementation, and what the other layers, the great work the other layers are doing. So actually when it comes to communication, low latency communication between two ECUs, then most of the work is done at the COM stack and the COM hardware layer, and not so much at the COM middleware protocols. Let's see on a real example how these layers interact or work. And what we've taken is a real example, let's say on an ECU, maybe the most challenging ECU type, the vehicle server, or HPC, high performance computer, or there are different names at different OEMs, but basically let's say that's the vehicle server. We start at the Linux user space. So we have two application processes. On the left side you see a blue box, that's a server which provides a service 1.1. And then on the right side there is another application process that runs a client service and the second server service. And yeah, here we have the green, the COM middleware layer. What we've used here, or using here, is the AUTOSAR adaptive SOMIB protocols. So that means that in each application process, there's a certain library, ARACOM library, and it takes care about IPC communication, so these connections to a third process, that's the ARACOM daemon. So for local communication, there are direct IPC sockets, but if you want to communicate to the network, then the ARACOM daemon takes care. And as you can see here on the screen, there are separate sockets, and if they have different priority, of course, there also needs to be separate queues and separate processing threads. So really to avoid that a high priority socket is blocked by a low priority one. At the next layer, let's say we're on a Linux-based device, so of course we're using a well-known TCP/IP stack of the Linux kernel, and here the priority from the middleware is mapped into an UDP socket priority. Actually, the let's say most important structure at the Linux kernel is these socket buffers, and this one gets the priority which is related to the middleware priority. And based on this socket buffer priority, later on the Linux kernel derives or sets the Ethernet header, the BCP field. And it also uses this socket buffer priority to select the related driver queue. Yeah, we are on a vehicle server, so it means there's not only one Linux, there are many virtual machines running Linux or a classic AUTOSAR. So we need to abstract the Ethernet hardware. We need to virtualize the Ethernet hardware. And that's done by software we've called virtual switch. So basically it's an hypervisor extension. It also provides different queues, so priority queue and best effort queue. And the frame processing, so from all the different virtual machines, you could imagine each virtual machine could have a priority queue and a best effort queue. Some virtual machines maybe only have best effort queues. And the virtual switch takes care that the frame processing between them is first done on priority. And if you have multiple virtual machines with the same priority or sockets with the same priority, then we are using a so-called interleaved weighted round-robin algorithm to have a fair processing of these different data streams. And finally, we are on the hardware layer, so finally we arrived, and there of course we have the high priority socket that's class A, credit-based shaping, and a standard best efforts socket or hardware queue. So in our test setup, on the top left, so server 1.1, that's a prioritized server. So it means he uses the priority sockets, here represented by filled circles, and it builds up such a bold line which has priority. And in our test setup, we have a second server that's on the right side, server 2.1, and that's only a low priority one, so best effort. And it uses best effort sockets, that's the empty circles. So both are able to transmit data, and if there's no interfering traffic, everyone is happy, everything is fine. So to make it a bit more complex, we created the traffic generator, which puts in a lot of low priority but interfering traffic. And what we could see is that, of course, server 2.1, the low priority servers, gets into trouble, has some frame loss, latency violations, while the server 1.1 with the bold line had no issue. So no frame drops and no latency violations. That's how we did it on this ECU type.
Okay, that being said, we see that in the vehicle server scenario, we are completely capable already to establish data path with guaranteed upper bound latency between communication partners. The drawback here is that those communication paths are purely statically configured with sender-receiver relationships defined upfront, so all the communication peers know each other. In a service-oriented setup, where basically the detection or the establishment, the binding between server and client is established dynamically by means of service discovery during runtime, this won't work. And therefore, we need some extension to the middleware that actually allows for negotiation of things like update cycle and maximum latency between the communication partners. And one possibility to do this, especially in a SOMIP-based environment, is to build this negotiation on an existing SOMIP PSD feature, namely the so-called configuration options. These configuration options are basically key value pairs or sequences of key value pairs actually that are part of the transmitted service discovery messages and that can carry actually arbitrary additional information related to a particular service. So this was a very generic design done by Lars, and we are going to leverage this here. And the idea is to actually standardize configuration options for the negotiation of maximum latency and update cycle. And so to attach maximum latency and update cycle configuration options to the service discovery messages in order to exchange this information between the communication peers. And the second ingredient here is we also want to provide the possibility to define the actual value of the maximum desired latency and of the update cycle via interface extensions to manipulate those values. And we have two variants in mind here. One variant is a configuration-based variant where we intend to, or where we plan to add additional arguments, additional attributes to existing configuration elements. For example, if we think about AUTOSAR adaptive platform, those would result in extending the meter model classes of the AUTOSAR manifest, for example, by appropriate configuration attributes. The other variant will be a dynamic variant where the desired update cycle and maximum latency are actually provided via the API. And here the intention is to extend the ARA-COM API of adaptive AUTOSAR by adding additional arguments to already existing methods, like, for example, the find service API of ARA-COM in AUTOSAR adaptive platform. Okay, yeah. So on the next slide, or on the next three slides, actually, we see a bunch of sequence diagrams that show that depict the complete picture here, where we see an interaction between a client application and a server application, depicted in blue boxes here, and the corresponding middleware elements depicted in green boxes here. And I'm going to show you three different scenarios. The first of all is the success scenario. So let's start at the right-hand side at the top. Here, the server application would actually tell the server middleware that it is capable of offering a particular service with a given provided update cycle. On the left-hand side, the client application would then instruct the client middleware to find exactly this service, providing a desired update cycle as an argument. This in turn will cause the client middleware to transmit a find service SOM-IP service discovery message containing the desired update cycle as a configuration option. Upon reception of this find service message, the server middleware could then check, okay, whether the desired update cycle, which is requested by the client, is actually compatible to the provided update cycle provided by the server, effectively meaning that it's slower. And if that is the case, then the server middleware responds with an offer service message containing the provided update cycle as a configuration option, and thereby indicating the positive or the success scenario that a matching service has been found also with respect to the desired update cycle. At a later point in time, the client application would then subscribe to a particular event, for example, of this offered service. And as part of the subscription, the client application via the API extension might also provide the desired maximum latency for received event notifications. This in turn will cause the middleware to transmit a subscribe event group message containing this desired maximum latency. The reception of this subscribe event group message will cause the server middleware to actually request a bandwidth allocation at the communication stack in order to actually meet this bandwidth, this desired latency. So the main input to this bandwidth reservation is the desired maximum latency and the size of the event data that needs to be transmitted in the course of an event notification. If this bandwidth reservation actually succeeds, the server middleware responds with a subscribe event group acknowledge message providing the provided maximum latency, again, as a configuration option in this message, and thereby then signaling success of the whole process. On the next two slides, we're going to see two different failure scenarios. The first one is a scenario where we have a mismatch in the update cycle. So basically, the client service looks for a desired update cycle that is effectively lower than what the server can provide. In that case, the find service message would contain the desired update cycle. The server middleware will detect, okay, that this desired update cycle cannot be matched by what the server is effectively capable of, and therefore the server middleware will omit the sending of the offer service message, and this in turn will serve as an indication on the client middleware to realize, okay, that the find service process has not succeeded, and the client middleware will then result will then indicate this failure of the fine service towards the client application. In the second scenario, this negotiation of the update cycle is something which goes well, so this succeeds. This is basically the upper half of this picture, but the reservation of the required bandwidth, which is in the lower right yellow box, will then fail, and this causes the server middleware to actually transmit the subscribe event group not acknowledged message to the client middleware, which then will indicate the failure again to the client application.
Yeah, after this AUTOSAR extension proposal, we are back now on the ComStack layer. So we need to configure and reserve the bandwidth and all network elements. And how we typically do it is as a static configuration. A more advanced approach, also in some cases used, is the stream reservation protocol according to 102.1q. So in this case, the bandwidth reservation is done in a distributed approach, individual at each switch. And there's a third option. Actually, we haven't implemented it now, but it's a really cool concept. So that's why we present it here. So it's a central vehicle network controller. And this is based on a software-defined networking architecture. So as you can see here in the diagram on the bottom, there's the vehicle network controller. And this one is an SDN controller, so it configures all the network elements, all these parameters. And it does that by using a, let's say, remote configuration interface, and our proposal is to use netconf-young for that, which is well known in the IT world. And how does this fully flexible reservation approach work? It works like this. The ComStack at the, let's say, server service or server ECU gets a request for bandwidth reservation. Actually, it's a layer 3 connection, and for that it's provided the server IP, the client IP, the data length of the data that will be transmitted, and of course the desired maximum bounded latency. And this request goes to the vehicle network controller. And as this one has configured all the network, he has all the knowledge, so it's perfectly easy for him to reserve the bandwidth, the required bandwidth in the network. Yeah, with that, let's say, to conclude our presentation, I would like to do it based on 4 aspects. So number 1, time-sensitive control data streams in a service-oriented architecture are service events with a defined update cycle and a maximum bounded latency. That means the key quality of service parameters is latency and update cycle. Second, the communication middleware needs to support this dynamic negotiation of update cycle and latency. And here we have done this AUTOSAR extension proposal. Actually, we plan to submit that, the AUTOSAR concept, by end of this year. And if you're interested and an AUTOSAR partner, just drop us an email. We would be more than happy to add you to the list of supporters for this new concept. And third, for quality of service, the whole data path is important. So, of course, all the data paths on the network, but also at the client and server ECU from the network interface up really to the application. And fourth, experiences from this quality of service implementation of a vehicle server we have shown here shows that time-critical data streams from a SOMA-IP server to a SOMA-IP client can be done with, let's say, no frame drops, no latency violations, even in case of heavy interfering traffic. It's just like Rettungsgasse. There's always way for important things. Thank you for your attention, and we're happy to take your questions.
Okay, thank you very much. I can see Max is already at the queue, so please.
Yeah, hey, I wanted to ask a question on your, I'll call it software-defined networking. And I mean, this is what we currently see being done in the industrial sector in 6802. But what is the level of complexity with adding these configuration protocols? We need security for these protocols in order to make sure people don't misconfigure our switches now. We're adding a whole layer of application complexity to that. Is there some, let's say, what's the ideal vehicle to do that in? Does it depend on what kind of a car I'm building? Or how do we justify that added complexity?
All right, just go back to the, I think you're referring
exactly.
to the third, let's say, concept. So let's say our response is based on concept. We have not implemented this approach, while the other tools we have. But there is some effort to create this central vehicle network controller. But if you have done that, that's a really great infrastructure element. So currently we have a lot of different protocols to configure the switches. In most of the cases is done by the local microcontroller where the switch is placed. So there's a VCU and on it it's a microcontroller and then a switch. And sometimes there's a smart switch firmware which does the configuration. In this approach, the point of view changes. It's really, let's say, you can configure the whole network from a vehicle network controller. And there's some effort. If we take the presentation from MAXEC, there is means to secure the communication. So I think there's an initial effort, but we will see that setup in the future because it's the most flexible one. All the distributed protocols we really like, these stream reservation protocols, end up to be very complex. And this SDN approach is at the end what IT world is showing in the data centers for many years. So I strongly believe that we will see these vehicle network controllers and then we can perfectly use them to implement a nice quality of service.
Okay, thank you. Then we have one online question. And Rudy is going to present it from the stage.
They asked me to present these from the stage. Comes from Volvo, Wab Bengtson, who's been at past events. Have you done any experiment on how this affects throughput of the comm stack? For example, number of frames per second. To what extent could hardware features reduce performance impact?
Let's see, we did some load tests on this vehicle server ECU. It was a 1 gigabit link which had multiple virtual machines and we were able to fully load it. So they used the full bandwidth of this gigabit link. I'm not exactly sure if I answered the question, so.
Well, there's no follow-up question so far, so.
Okay.
Okay, then thank you very much for your presentation.
Oh, we have one more question in the back? Or?
Yeah.
Oh, sorry, you have, yeah, go ahead. Apologies, I didn't see it.
Yeah, hi, Jürgen Scheuring, TSN Systems. I have a question about the shapers you believe in. I think this concept that you show here with the central network configuration is actually intended to manage the complexity with QBV shapers, right? Because then the scheduling is really complex. And on the other side, you mentioned that you're working with QAV shapers where you can make your life much more easy with SRP. So I want to know what you believe in. What is the market going in the future?
Yeah, I think
we'll have a lot more on those in the next actually session. So I'd really like to take, in terms of the time, I'd like you to take that question in the breaks to those two and listen intensively to not the questions before, the presentations before lunch, but after lunch. We have a whole session on shapers. Okay, thank you.